In our previous example, we saw a technique that was useful for bounding summations above and below when you did not have a nice formula. To practice bounding above and below, we're going to work with the summation. However, we need to add some small asterisks here. Remember, in the previous example, we had log base 2 of I as the summand. That summand was an increasing function of I. However, here, we have minus I squared inside. As I gets bigger, that gets smaller. This summand is a decreasing function of I. Therefore, we will have to be careful when bounding this above and below. So, T of n is equal to that summation, which goes from 0 to n minus 1, of quantity n squared minus I squared. Our technique for bounding above was to replace each term with the largest possible term. Remember, that is a decreasing function of I. Therefore, the largest possible value would be the first value of the summation. If it's decreasing, each subsequent value of I is subtracting a larger value of I. Therefore, to make this as big as possible, I would plug in the smallest possible value of I. So, I bound this above by replacing I with the smallest value of I within the range. That is, in this case, replace it with 0. And now, we have removed I from the problem, just as we did in the previous problem. By choosing a particular value of I, we are effectively replacing each term with the largest term. So this is less than or equal to. Now that we have done this, we no longer have any I inside of the summation. So we now have a fixed quantity so far as the summation is concerned. We can take that fixed quantity and multiply by the number of terms in the summation. The number of terms in the summation, remember, again, is the top bound minus the bottom bound plus 1 times the summand. We're adding up n squared that many times, n minus 1 minus 0 plus 1 times. This is equal to n minus 1 plus 1 cancel times n squared, which is n cubed. So it is in big O of n cubed because we bounded it above by a constant, in this case, 1 times n cubed. We now need to find some way to bound it below by the same thing. Our technique that we used in the previous videos will still be very reasonable. However, we need to add a small asterisk just like we did here. Again, because it's decreasing, we're going to need to slightly modify our technique for bounding below. So, just as we did in the past, we're going to begin by writing down the summation. T of n is equal to the sum from I equals 0 to n minus 1 of n squared minus I squared. We're going to split the summation in the middle somewhere. I'm going to go from 0 to n divided by 2 of n squared minus I squared plus the sum from I equals n divided by 2 plus 1 to n minus 1 of the same summand, n squared minus I squared. And now we need to bound this below. Remember, the technique we used before was to plug in the bottom bound of the summation because it was an increasing function of I. Plugging in a value of I that is smaller than everything in the range made it small. However, this is a decreasing function. So, in order to make these things smaller, we'd have to plug in large values of I. Let's see what I mean by that by writing out the terms of one of these summations. This first summation is n squared, then plus n squared minus 1 squared, plus n squared minus 2 squared, plus keep going until we plug in n squared minus n over 2 quantity squared. Notice that each term is getting smaller as you add them up. So to bound this below, I cannot plug in the bottom bound as we did for our log example we saw in the past. However, each term is definitely bigger than the final term, which is the smallest because it's subtracting the largest value. A similar thing holds for the second summation. So, just like we did when we bounded below for that log example, we are going to remove one of these summations. In the log example, what we did is we dropped the first summation. The reason for doing that is that that was the smaller summation. We want to drop the smaller of the two summations. In this case with the log, those first terms were smaller than the second half of the terms. However, when you have a decreasing function, as we do here, the first half of the terms are the bigger terms of the summation. So, to bound this below, what we're going to do is drop the second summation. We're going to remove this summation. because it is a decreasing function of I, we want to keep the larger of the two. We'll explain a bit more after we finish this problem, but for now, take for granted the fact that we're going to keep the larger of the two. So we have the sum from I equals 0 to n over 2 of n squared minus I squared. We are now going to make it yet smaller still by replacing every term in the summation with the smallest term. Having written out the terms here, we can see that the smallest is definitely the final term of the summation. So this is greater than or equal to the sum from I equals 0 to n divided by 2 of n squared minus replace I with the largest value that it obtains on that interval of values. Because it is decreasing, the largest possible value will make it as small as possible. Therefore, we now have no more i's inside of the summation. That quantity, for all intents and purposes, is fixed for that summation. Therefore, we need only multiply that quantity by the number of terms in the summation. So, this is greater than or equal to the top bound of the sum minus the bottom bound plus 1. N over 2 minus 0 plus 1 is n over 2 plus 1, times the sum and, the thing inside of the summation. This is, again, the number of terms multiplied by the thing that's inside of the summation, which in this case is n squared minus n squared divided by 4. And just as we have done several times in the past, that plus 1 that appears is going to be tedious to deal with, so we're going to drop it. While bounding below, you can always, always, always drop positive constants. So this is greater than or equal to n over 2 times quantity. N squared minus n squared over 4 is 3n squared over 4. So this is 3 over 8 n to the third, which is a number times n to the third, which is all we needed to do since we bounded it above by a number times n cubed. It was in big O of n cubed. We have now bounded it below by a number times n cubed. Therefore, it is in big omega of n cubed. So we can now tell the reader, since t of n, the quantity we started with, is in big O of n cubed, and t of n is in big omega of n cubed, thus t of n must be in theta of n cubed. Now, we didn't actually have to make any assumptions about n to do the stuff we did here, so we maybe should go back up to our splitting the summation trick we did and just make sure that it made any sense. So, for any value of n, was this a well-defined thing? We just needed that n over 2 plus 1 was bigger than 0, so let's write that down. When is it the case that n over 2 plus 1 was bigger than or equal to 0? That is n bigger than or equal to negative 2. Math seems to check out, so we should be okay. So, we have no major concerns about the size of n. We don't have any particular n naught to be concerned about for our definitions, so we don't need to specifically comment on it. Now, we have that this summation is in n cubed. Why did we keep the bigger of the two summations? I said we would hold off on that for now. Why did I drop the second half of the terms here? Why did I do that? Because we are trying to bound this above and below by the same function, which means, in some sense, you want your upper bound to be as small as possible and your lower bound to be as big as possible, so they meet in the middle. To show that something is in theta, you want that the upper bound and lower bound match exactly. If you've taken calculus, this is similar to the squeeze theorem. You want to bound it above and bound it below in such a way that they end up meeting in the middle. You want the upper bound to be very small and the lower bound to be very big, which seems counterintuitive. The reason that it makes sense is that you need that they meet in the middle. So, we keep the larger half of the terms to keep the lower bound big enough such that it will match the upper bound. If we had kept the second half, we would make it too small and would not be able to make it match the upper bound successfully. So we must keep the first half, the larger half of the terms, to guarantee that the bounds match exactly.